Hello there, and welcome to Midnight Science, where curiosity slows down, the lights grow soft, and science takes the long, quiet road towards sleep. Tonight, we are going to talk about something you have been experiencing since the moment this video began. Time. Even now, as you listen, time is passing. A few seconds have already disappeared behind us. A few more are arriving. The present keeps changing shape. Words appear, then become memory. A breath comes in, then leaves. A thought rises, then fades. And no matter how still the room may feel, time continues moving in one direction, forward. At least, that is how it feels. You can pause a video, you can rewind a song, you can look at an old photograph, you can remember a voice, a place, a day, or a version of yourself that no longer exists in the same way. But you cannot step backward into yesterday. You cannot unbreak a glass by simply waiting. You cannot watch smoke gather itself neatly back into a candle. You cannot stir milk out of coffee once it has mixed. Everyday life seems to have a direction. Eggs crack, but do not naturally uncrack. Ice melts in a warm room, but a puddle does not usually gather itself back into a perfect cube. A cup of tea cools down, but it does not suddenly borrow heat from the room and become hot again. Dust spreads, perfume diffuses, footsteps fade, stars burn their fuel, bodies age, memories accumulate. The world appears to move from before to after, from cause to effect, from order into a more complicated kind of disorder. And yet, deep inside physics, there is a puzzle. Many of the basic laws that describe motion do not seem to care very much about the direction of time. If you watched a simple movie of two billiard balls colliding on a perfectly smooth table, and then played that movie backward, the motion might still look physically possible. Atoms move, particles collide, equations work. In many microscopic situations, the laws allow motion forward and backward. So why does the world we experience feel so one way? Why do we remember the past, but not the future? Why do causes come before effects? Why does a broken glass not leap from the floor, reassemble itself, and land safely on the table? Why does time seem to have an arrow? That is the quiet question for tonight. Why does time only move forward? Before we begin, I would love to know where you are listening from tonight. Is it late where you are? Are you already in bed? Or just letting the day soften around you? And if these calm journeys through science help you relax, study, or drift towards sleep, consider liking the video and subscribing to Midnight Science. It helps this small corner of quiet curiosity find others who enjoy learning softly in the dark. Now, get comfortable. Let your shoulders settle. Let your jaw relax. Let the room become a little quieter around you. There is no need to remember every equation. There is no need to hold on to every term. You can simply listen, rest, and let the idea of time unfold slowly in the background. Tonight, we will follow the arrow of time through some of the most important ideas in physics. We will begin with the strange fact that many microscopic laws appear reversible. Then we will look at ordinary things, like broken glass, cooling tea, and milk mixing into coffee. We will meet entropy, one of the most important and misunderstood ideas in science. We will see why disorder is not just missenses, but probability. We will explore the second law of thermodynamics, the rule that gives time its most familiar direction. We will ask why we remember the past and not the future. And near the end, we will widen the view all the way out to the universe itself, to the early cosmos, the distant future, and the possibility that time's arrow began with the conditions of the Big Bang. This is a story about physics, but it is also a story about experience. Because time is not only something written in equations, it is something we live inside. You never see time directly. You see change. A shadow moving across a wall, a candle growing shorter, a star shifting in the sky, a face becoming older in a photograph, a cup cooling beside a bed, a season passing, a memory becoming softer at the edges. Time is the name we give to the ordering of these changes. The universe does not hand us a clock with an explanation. It gives us events, one after another, and from those events, we build the feeling of before and after. So tonight, we are going to follow that feeling carefully, not quickly, not urgently, but gently. From tiny particles to the large history of the universe. From a broken cup on the floor to the fate of distant stars. From your quiet room to one of the deepest questions in physics. Why does time have a direction? To begin, we must look at something surprising. At the smallest scales, the universe seems far less concerned with past and future than we are. Time's arrow may feel obvious in daily life, but in the equations of motion, it begins as a mystery. To understand why time feels one way, we first need to notice something strange. Many of the basic laws of physics do not obviously prefer one direction of time over the other. That may sound impossible at first. After all, everything in ordinary life seems to move from past to future. A cup falls and breaks. A candle burns down. A hot drink cools. A person grows older. A memory forms after an event, not before it. But when physicists look at some of the simplest motions in nature, the direction of time is not always written into the equation. Imagine two billiard balls on a perfectly smooth table. One ball rolls forward, it strikes another ball. The second ball moves away. If you filmed this collision and played it normally, it would look like ordinary physics. A ball moves, it collides. Momentum and energy are transferred. Now imagine playing the same film backward. Newton's laws often lack a built-in arrow pointing to the future. They describe relationships between position, velocity, acceleration, force, and mass. If the motion is reversed carefully enough, the equations can still work. This is one of the first pieces of the puzzle. At the level of clean, ideal motion, physics can be tied. They describe relationships between position, velocity, acceleration, force, and mass. If the motion is reversed carefully enough, the equations can still work. This is one of the first pieces of the puzzle. At the level of clean, ideal motion, physics can be tied. A planet orbiting a star could be imagined moving forward in its orbit. Or, if every velocity were reversed exactly, it could trace the same path backward. The gravitational law would still describe the motion. A pendulum swinging in a vacuum with no friction could swing one way, then the other, and a reversed movie of that motion would not immediately violate the basic law. A particle moving through empty space could be reversed. A simple collision could be reversed. In these ideal cases, the laws do not loudly announce a preferred direction. They allow the motion, forward, backward. Symmetrically, this does not mean time is not real. The future doesn't already behave like the past in ordinary life. It means some of the deepest equations describing microscopic or idealized motion are surprisingly neutral about time's direction, and that creates a problem. If small parts of the universe obey laws that work both ways, why does the large world seem to move only one way? Why does a bouncing ball video look fine forward and backward, while shattered glass reassembling itself looks absurd? Why does one kind of process feel reversible, while another feels impossible? The answer begins with the difference between microscopic laws and macroscopic experience. Microscopic means very small. Atoms, molecules, particles, small collisions, tiny motions. Macroscopic means large enough for us to experience directly. Cups, rooms, bodies, clouds, planets, engines, ice cubes, coffee, smoke. At the microscopic level, a great deal of motion is made of particles interacting according to laws that may be reversible. Molecules bounce, atoms collide. Energy moves from one particle to another. If you knew every position and every velocity perfectly, and if you could reverse them all exactly, many systems could in principle run backward. But in the macroscopic world, we never control every particle. A cup is not one object in the deep physical sense. It is an enormous collection of atoms arranged in a particular structure. A cup falling from a table is not just a smooth shape moving through space. It is billions upon billions of particles held together by electromagnetic forces. When it hits the floor and breaks, energy spreads into cracks, sound, heat, vibrations, tiny fragments, motion in the air, motion in the floor, and disorder in the arrangement of the material. To reverse that event, it would not be enough to say, let the cup go backward. Every tiny piece would need to move in exactly the right way. Every vibration would need to return. Every sound wave would need to come back from the walls. Every bit of heat would need to collect itself. Every atom would need to cooperate. The fragments would need to rise from the floor, find their old positions, reconnect, and return to the table. The laws may not forbid this in the simplest imaginable mathematical sense, but the arrangement required is so unbelievably specific that it never happens in ordinary life. Here, the puzzle begins to shift. The arrow of time may not come from a simple law saying time must go forward. It may come from probability, from the difference between what is possible and what is overwhelmingly likely. A broken cup reassembling is not impossible in the same casual way that a square circle is impossible. It is physically allowed only in a fantastically precise, fantastically unlikely arrangement of microscopic motions, and the universe does not usually choose fantastically unlikely arrangements. It follows the overwhelmingly likely ones. This is where time begins to look less like a command and more like a statistical direction. The future is the direction in which overwhelmingly likely things tend to happen. A hot object shares heat with a cooler room. Gas spreads through a container. Perfume diffuses through air. Milk mixes into coffee. Ice melts in warm water. The opposite processes are not easy to produce naturally because they require an enormous number of microscopic details to line up just right. Consider perfume in a room. When a small amount of perfume is released, its molecules begin concentrated in one region. Then they move. They collide with air molecules. They spread. After a while, the scent may be detectable throughout the room. Now, imagine the reverse. All the perfume molecules, scattered throughout the room, suddenly move in just the right directions so that they gather back into one small region. The laws of motion for individual molecules may allow such paths if all velocities are perfectly arranged, but in practice, the number of possible spread-out arrangements is vastly larger than the number of concentrated arrangements, so spreading happens naturally. Unspreading does not. This is the quiet, mathematical heart of the arrow of time. There are far more ways for things to be mixed than unmixed. Far more ways for energy to be spread out than concentrated. Far more ways for a broken object to remain broken than to reassemble. Far more ways for a system to become less specially arranged than to become more specially arranged by accident. The universe does not need to force time forward with a giant cosmic hand. It only needs many particles, many possible arrangements, and probability. Then the arrow appears. But before we reach entropy directly, let us stay with the puzzle a little longer, because it is one of the strangest facts in physics. At small scales, motion can often be reversed in principle. At large scales, reversal becomes practically impossible. This is not because the large world uses completely different ingredients. The large world is made of the small world. Cups are made of atoms. Air is made of molecules. Bodies are made of cells, molecules, atoms, and particles. The macroscopic world is built from microscopic pieces, so the question becomes sharper. How can reversible microscopic laws produce irreversible macroscopic experience? How can a universe made from time-symmetric rules create a world where time feels one way? This question troubled physicists deeply. It is connected to the foundations of statistical mechanics, the branch of physics that explains heat, temperature, pressure, and entropy in terms of microscopic particles. Statistical mechanics is one of the great bridges in science. It connects the small invisible motions of particles to the large visible behavior of matter. It explains why gases have pressure, why heat flows, why temperature means something physical, why a cup of tea cools, why ice melts, why engines have limits, and why time seems to move forward. The key is that we do not track every molecule, we use averages. Temperature is an average measure of microscopic motion. Pressure comes from countless molecules colliding with surfaces. Heat flow comes from energy being exchanged among huge numbers of particles. When enough particles are involved, probability becomes extremely reliable. A single molecule might behave unpredictably. A trillion molecules behave statistically. They follow patterns, not because each molecule knows the plan, but because large numbers make some outcomes overwhelmingly more likely than others. Imagine flipping a single coin. It might land heads, it might land tails. Now, imagine flipping a trillion coins. You would expect roughly half heads and half tails. Not exactly half, but very close. The more coins you flip, the more stable the pattern becomes. The same kind of thinking applies to particles. One molecule might wander anywhere. Gas made of countless molecules will almost certainly spread to fill its container, not because spreading is commanded, because there are so many more spread-out arrangements than clustered arrangements. In this sense, the arrow of time is a story about numbers, so large that probability becomes destiny, not absolute destiny in a philosophical sense, but physical certainty for all practical purposes. A room full of air will not suddenly gather into one corner and leave the rest of the room empty. The molecules could, in an abstract mathematical sense, all happen to move that way, but the probability is so tiny that it is effectively zero. You could wait longer than the age of the universe and still never see it. This is why everyday time has such a steady direction, not because each particle has a tiny arrow painted on it, but because collections of particles move from rare arrangements toward common arrangements, from special conditions toward ordinary ones, from concentrated energy toward spread-out energy, from low entropy toward higher entropy. Entropy is the word we will soon need, but for now, we can describe the idea without naming it too quickly. Imagine a deck of cards arranged perfectly by suit and number. That is a special arrangement. There are only a few ways to make the deck look ordered like that. Now, shuffle it. The cards become mixed. There are enormously many ways for the deck to be mixed. If you keep shuffling, you do not expect the deck to return naturally to perfect order. It could happen in principle, but the odds are so small that it might as well be impossible. The deck moves from a rare arrangement to a common one. That is the flavor of entropy, the flavor of time's arrow. The physical world is full of shuffled decks, air molecules, water molecules, heat energy, fragments of glass, dust in a room, light from stars, all moving from rare, special arrangements toward more common, more spread out, more probable arrangements. This is the strange puzzle of time. The laws underneath may often be reversible, but the world built from countless particles becomes irreversible in practice. The arrow of time is not obvious in a single particle. It emerges in crowds, in collections, in systems too large to track completely. In the difference between one possible arrangement and almost unimaginably many others. And now that we have seen the puzzle, we can bring it closer to ordinary life. A cup that breaks, milk mixing into coffee, a warm drink cooling beside a bed. These are not just familiar events. They are small demonstrations of the arrow of time. They show us entropy before we ever write an equation. And in the next scene, we will look at those ordinary examples carefully. Because broken glass and mixed coffee may know more about time than they first appear to. The arrow of time is not something we usually notice as an abstract law. We notice it in ordinary things: a glass falling from a table, milk spreading through coffee, steam fading from tea, a scent slowly filling a room, ice melting in a warm drink. These events feel natural in one direction and strange in reverse. That strangeness is the clue. Imagine a glass sitting near the edge of a table. For a while, nothing happens. The glass is whole. Its atoms are arranged in a stable structure. Its shape is familiar. A curved surface, a rim, a base, a hollow space inside. Then the glass is knocked off balance. It falls. Gravity accelerates it downward. It hits the floor. A sharp sound spreads through the room. The glass breaks into fragments. Some pieces slide, some bounce. Tiny shards scatter. Energy moves into the floor, into the air, into sound waves, into heat, into microscopic vibrations inside the material. Now ask a simple question. Why does this feel like the future? Why does the falling and breaking feel normal, while the reverse feels absurd? A reversed movie would show tiny shards on the floor beginning to tremble. Sound waves would gather from the walls and air. Heat would collect from the surroundings. Fragments would slide together. Cracks would close. The glass would rebuild itself. Then it would leap upward and settle gently on the table. Nothing about that reverse story matches ordinary experience. It feels wrong, not just unlikely in the everyday sense, almost offensive to common sense. And yet, at the level of atoms, the difference is subtle. The broken glass is still made of the same atoms. The energy has not vanished. The laws of conservation still apply. Energy is still energy. Momentum is still momentum. Matter is still matter. What changed is the arrangement. Before the fall, the atoms of the glass were arranged in a very particular way. They formed one object, a cup shape, a smooth structure, a low number of large pieces. After the fall, the same matter is arranged in a much less special way: fragments, shards, vibrations, heat, sound, tiny cracks, dust-like pieces. Energy spread through many channels. There are vastly more ways for glass atoms to be scattered and broken than for them to be arranged as one perfect cup. This is why the broken state is so much easier to reach. A whole glass is a special arrangement. A broken glass is one of many possible arrangements. If you've dropped a glass 1,000 times, it could break in many different patterns. Large fragments, small fragments, a crack down the side, a shattered rim, pieces spread to the left, pieces spread to the right, powdered edges, sharp triangles, curved pieces. The exact broken pattern can vary enormously. But there are far fewer ways for all those atoms to form the original, intact shape. The intact glass is specific. The broken glass is flexible. It has many possible versions. Time seems to move from the specific toward the flexible, from the rare arrangement toward the common one, from the delicate order toward the many possible broken states. This is one of the central ideas behind entropy. But before defining entropy directly, let us look at another example. A cup of black coffee, still, dark, warm, on the table. Now imagine adding a small stream of milk. At first, the milk enters as a pale cloud. It curls through the darker liquid. White ribbons stretch and fold. They form branching shapes. For a moment, the coffee and milk are partly separate. You can still see structure, light and dark regions, swirls, boundaries. Then the motion continues. The liquids stir each other. Molecules move. Currents fold the milk into the coffee. Diffusion spreads the particles. Soon the cup becomes a more uniform brown. The milk has mixed. Now imagine the reverse. A cup of evenly mixed coffee begins to unmix. Brown liquid separates into dark coffee and pure white milk. The milk gathers itself into a neat stream. The stream rises upward out of the cup. The coffee returns to its original black stillness. Again, the reverse feels impossible. Not because the molecules are forbidden from moving in those directions one by one, but because the required coordination is unbelievably precise. Every milk molecule and coffee molecule would need to move in just the right way. Currents would need to reverse. Tiny thermal motions would need to cooperate. The mixed liquid would need to find one of the very few arrangements where milk and coffee are separate again. But there are far more ways for milk and coffee to be mixed than unmixed. Once mixed, the system has moved into a much more probable state, a more common arrangement, a state with less visible separation, a state that can be created in countless microscopic ways. This is why mixing is easy and unmixing is not. The spoon does not need to know where every molecule is. It only needs to stir. Random molecular motion and fluid currents do the rest. But to unmix the coffee, randomness is not enough. You would need control. Immense control. Control over each molecule. A kind of microscopic choreography so precise that no ordinary process can perform it. This tells us something important. The arrow of time is not only about things breaking, it is also about things mixing. Breaking and mixing are cousins in the language of entropy. In both cases, a special arrangement becomes less special. The original glass is one specific arrangement. The original coffee and milk are partly separated. After time passes, the glass fragments are spread out. The milk and coffee are mixed. Both systems have moved toward states with many more possible microscopic arrangements. This is why a broken glass and mixed coffee belong to the same story. They are different examples of probability becoming visible. Now, consider a hot cup of tea in a cool room. At first, the tea is hotter than the air around it. Its molecules, on average, are moving with more thermal energy. The room air is cooler, the cup is cooler, the table is cooler. Over time, heat flows from the tea into the cup, the air, and the surroundings. The tea cools down. The room warms by a tiny amount. Eventually, the tea approaches the temperature of the room. This feels normal. A hot drink cools. But the reverse does not happen naturally. A lukewarm cup of tea does not suddenly gather heat from the surrounding room and become hot while the room becomes slightly cooler. That reverse process would not violate the conservation of energy if arranged perfectly. Energy could, in principle, move from the room into the tea. But the problem is probability. Thermal energy in the room is spread across an enormous number of molecules. For the tea to heat up by itself, countless microscopic motions would need to line up so that energy flowed from the cooler surroundings into the warmer drink. This would be a move from a more probable distribution of energy to a less probable one. Not impossible in a tiny fluctuation for very small systems, but for a cup of tea in a room, so unlikely that it is never seen. Heat naturally flows from hot to cold, because there are vastly more ways for energy to be shared than for it to remain concentrated. The hot tea begins as a special condition. Energy is concentrated in the tea. The final state is more ordinary. Energy is more evenly spread between tea, cup, air, and room. Again, time points towards spreading, not because heat has a tiny compass, but because spreading is overwhelmingly more likely. The same idea appears when a scent fills a room. Imagine a small amount of perfume released into still air. At first, many scent molecules are concentrated near one place, near the bottle, near a wrist, near a flower. Then they move. They collide with air molecules. They bounce, they drift, they spread outward. After a while, the scent is not confined to one small region. It has diffused. Diffusion is the spreading of particles from regions of higher concentration to regions of lower concentration. It happens because particles are always moving, and random motion tends to spread them out. Now reverse it. All the scent molecules scattered through the room spontaneously gather into one small region again. The air clears everywhere else. The perfume returns to its source. Again, this would require extraordinary coordination. The molecules would all need to move in just the right directions at just the right times. The spread out state has far more possible arrangements. The concentrated state has far fewer. So diffusion gives us another arrow, from concentration to spread, from rare to common, from special to ordinary. A melting ice cube tells the same story in another form. An ice cube in warm water begins with structure. Water molecules in the ice are arranged in a crystal lattice. They vibrate around fixed positions. The surrounding liquid water is warmer. Energy flows into the ice. The crystal structure breaks down. Molecules leave the lattice and join the liquid. The ice melts. Eventually, the water becomes more uniform in temperature. The reverse would be strange. A glass of water at room temperature would suddenly gather thermal energy in just the right way so that some molecules arranged themselves into a neat cube of ice, while the surrounding water became warmer. Again, not the normal path. Freezing can happen if heat is removed, if the environment is cold enough, if energy leaves the water, but spontaneous reformation of an ice cube in warm water is not what probability favors. The key pattern is now appearing again and again. Glass breaks, coffee mixes, tea cools, perfume spreads, ice melts. In each case, the reverse is not forbidden, because matter cannot move that way in principle. It is forbidden in practice by probability. The number of microscopic arrangements corresponding to the ordinary final state is vastly larger than the number corresponding to the special initial state. This is the bridge from experience to entropy. Entropy is often described as disorder. That description is partly useful, but it can also be misleading. Disorder makes us think of messy rooms, scattered papers, or laundry on a chair. Physics means something deeper. Entropy measures how many microscopic arrangements correspond to the same overall condition. A high entropy state is one that can be realized in many microscopic ways. A low entropy state is one that can be realized in fewer microscopic ways. A whole glass has low entropy compared with shattered fragments. Separated milk and coffee have lower entropy than mixed coffee. Hot tea beside a cool room has lower entropy than tea, and room sharing energy more evenly. Perfume concentrated in one corner has lower entropy than perfume spread through the room. The direction we call the future is the direction in which entropy tends to increase. But notice the word tends. This is not like a traffic sign that forces every molecule to obey. It is a statistical tendency so strong that, for large systems, it becomes a practical certainty. In small systems, fluctuations can happen. A few particles may briefly move in surprising ways. But in large everyday systems, with enormous numbers of particles, the statistical pattern is overwhelming. This is why the arrow of time is so reliable. A glass does not coffee does not unmix. Tea does not heat itself from a cooler room. Perfume does not gather itself back into the bottle, not because reverse motion is mathematically unimaginable, because the odds are too small. The universe is not choosing drama, it is following statistics. This can feel a little strange. We usually experience time as something fundamental, flowing like a river. But in thermodynamics, time's direction appears through the behavior of many particles. The river is made of probabilities. Every second, the world moves through microscopic arrangements. Some arrangements are rare and special, others are common and numerous. If a system begins in a rare arrangement, it will almost certainly move toward a more common one. That movement gives time a visible direction. This raises another question. Why did the system begin in a rare arrangement at all? Why was the glass whole before it broke? Why was the milk separate before it mixed? Why was the tea hot before it cooled? Why was the early universe in a low entropy state? That final question will become important later. But for now, the ordinary examples have done their work. They show us the arrow of time in the room around us, not as philosophy first, as physics. A glass on a table contains atoms in a delicate arrangement. A cup of coffee contains molecules waiting to mix. A hot drink contains concentrated thermal energy. A scent contains particles concentrated in one region. Each one begins in a state that is more special than the state it tends to become. And as the system evolves, the specialness fades. The arrangement becomes more probable. Energy spreads, matter mixes, fragments scatter, the future appears. There is something quiet about this idea. Time does not need to shout. It does not need a visible line in the air. It reveals itself in small, irreversible changes. In the cooling of a cup, in the fading of steam, in the spreading of a scent. In the way a broken thing stays broken, in the way milk disappears into coffee and becomes part of a new whole. These examples are close to us. They are ordinary enough to ignore, but each one carries one of the deepest principles in physics. The universe moves from less probable arrangements toward more probable ones, from lower entropy toward higher entropy, and in the next scene, we will finally give that principle its proper name. Entropy, the hidden direction behind the arrow of time. Entropy is one of the most important ideas in physics. It is also one of the easiest to misunderstand. People often say that entropy means disorder, and that is not completely wrong. A messy room has more entropy than a perfectly arranged room, in a loose everyday sense. A shattered glass seems more disordered than an intact glass. Milk mixed into coffee seems more disordered than milk and coffee kept separate. But in physics, entropy is not simply messy. It is not just clutter. It is not the universe being untidy. Entropy is more precise and more interesting. Entropy is connected to the number of microscopic ways a system can be arranged while still looking the same from the outside. That sentence is worth taking slowly. The microscopic arrangement means the exact positions and motions of all the particles, every molecule, every atom, every tiny piece. The macroscopic description means the large-scale features we can observe without tracking every particle, temperature, pressure, volume, shape, color, whether a glass is whole or broken, whether coffee is mixed or unmixed, whether gas is concentrated in one corner or spread through a room. A macrostate is the big picture. A microstate is the hidden detail. Entropy tells us how many microstates correspond to a macrostate. A low-entropy macrostate has relatively few possible microstates. A high-entropy macrostate has vastly many possible microstates. This is the heart of the idea, not machines as a mood, but multiplicity. How many ways can the hidden pieces be arranged while the large-scale situation still looks the same? Imagine a deck of cards. If the deck is perfectly ordered by suit and number, that is a very special arrangement. There are not many ways for the deck to be perfectly ordered. In fact, if we define the order very strictly, there may be only one exact arrangement that counts. Now shuffle the deck. The cards become mixed. There are many, many ways for a deck to be mixed. So many that the number is almost absurd. Most arrangements of cards look random. Only a tiny fraction look neatly ordered. If you shuffle the deck again, it will probably remain mixed. Not because order is forbidden, not because the cards dislike order, but because mixed arrangements outnumber ordered arrangements by an enormous amount. The ordered deck is rare. The shuffled deck is common. Entropy is related to this difference. The future usually carries systems from rare arrangements toward common ones, from special arrangements toward ordinary ones, from low entropy toward higher entropy. Now think about a gas in a box. Imagine all the gas molecules somehow gathered in the left half of the box. That is a special condition. There are many molecules, but they are all restricted to one side. Now remove the divider. The gas spreads out. Soon, the molecules fill the whole box. From our large-scale view, the gas has expanded. It has become more evenly distributed. Now ask, why does the gas not spontaneously gather itself back into the left half? Each molecule is still moving. Each molecule is still obeying physical laws. In principle, a molecule can move left or right. Nothing about a single molecule forbids it from being on the left side. But for all the molecules to gather on the left side at once, their motions would need to line up in a very special way. There are far more arrangements where the molecules are spread throughout the box than arrangements where all of them are confined to one half. So the spread out state is overwhelmingly more likely. The gas expands because expansion leads to a macrostate with far more microstates. That is entropy. A simple container of gas becomes a quiet lesson in probability. The same idea applies to heat. Temperature is related to the average kinetic energy of particles. In a hot object, the particles have more thermal energy on average. In a cold object, they have less. When a hot object touches a cold one, energy is exchanged. Particles in the hot object interact with particles in the cold object. Energy spreads. Eventually, both objects approach a common temperature. This is the normal direction. Hot to cold. Concentrated thermal energy to shared thermal energy. A hot cup of tea cools in a room because there are far more ways for the energy to be spread between tea and room than for it to remain concentrated in the tea. The reverse would require many particles in the room to send energy back into the tea in a coordinated way. Again, not mathematically impossible for a tiny system in a tiny fluctuation. But for a real cup of tea and a real room, overwhelmingly unlikely. The tea cools because the high entropy direction is the direction of energy spreading. Entropy does not mean that everything becomes useless instantly. It means that energy and matter tend to move toward more probable arrangements. Sometimes that looks like disorder. Sometimes it looks like mixing. Sometimes it looks like cooling. Sometimes it looks like expansion. Sometimes it looks like the loss of a special pattern. A glass before breaking is a special pattern of atoms. After breaking, there are many possible scattered arrangements. A cup of coffee before mixing has a visible separation between milk and coffee. After mixing, there are many possible arrangements that all look like uniform brown liquid. A hot drink has energy concentrated in one place. After cooling, the energy is more spread out. Each example points in the same direction. More possible microstates, higher entropy. The word entropy comes from thermodynamics, the study of heat, work, energy, and matter. In the 19th century, scientists studying steam engines discovered that heat could not be converted into useful work with perfect efficiency. There were limits. Some energy always became unavailable for useful work. Heat naturally flowed from hot bodies to cold bodies. Engines needed temperature differences. No engine could turn all heat into work without leaving other changes behind. The idea of entropy emerged from these studies. At first, entropy was a thermodynamic quantity. It helped describe heat flow and the limits of engines. Later, through the work of scientists such as Ludwig Boltzmann, entropy gained a deeper microscopic meaning. Boltzmann connected entropy to probability, to the number of microscopic arrangements, to the hidden world of atoms and molecules. This was a profound step. It linked heat, temperature, and time's error to the statistical behavior of particles. On Boltzmann's tomb, there is a famous equation, S equals K times the logarithm of W's is entropy. K is Boltzmann's constant. W represents the number of microscopic arrangements corresponding to a macroscopic state. The exact symbols matter less for our quiet journey than the idea behind them. Entropy increases when there are more ways for the system to be arranged microscopically. A high entropy state is a state with many possible hidden arrangements. A low entropy state is more special, more constrained, less common. This is why entropy is often associated with probability. A system does not need to know where to go. It simply moves through the space of possible arrangements. And because high entropy arrangements are so much more numerous, the system almost always ends up there. Imagine dropping a handful of sand onto a table. The grains scatter. There are countless ways for the sand to be scattered. Now, imagine the reverse. The scattered grains rise and gather into the exact shape of your hand. Possible in a fantasy, not expected in physics. Not because gravity or motion forbids every grain from moving upward in some imaginary reversal, but because the required microstate is fantastically specific. Entropy is the measure of how unspecific a state can be. The more ways there are to produce the same large-scale appearance, the higher the entropy. This is a subtle but powerful shift. Disorder is only the surface impression. The deeper idea is counting possible arrangements. A tidy room seems low entropy because objects are in special places. Books on shelves, clothes folded, papers stacked. A messy room seems high entropy because there are many ways for objects to be scattered and still count as messy. But rooms are complicated, and human ideas of order are subjective. Physics uses cleaner examples: gas molecules, heat flow, mixing liquids, particle distributions, energy states. Still, the room analogy helps. There are far more ways for a room to be messy than perfectly arranged. That is why, without effort, rooms tend to become messy. Order requires selection, maintenance, energy, attention. Disorder arrives easily because many arrangements qualify. In physics, the same logic becomes universal. A low entropy state is special. To create it, something must prepare it. A refrigerator creates a cold region by using energy and releasing heat elsewhere. A living organism maintains internal order by taking in energy and releasing waste heat. A person cleans a room by doing work. A star forms from gravitational collapse, but radiates energy away and increases entropy elsewhere. Local order can increase, but the total entropy of the larger system still tends to increase. This is important. Entropy increasing does not mean every place becomes more disordered at every moment. Snowflakes can form, crystals can grow, living cells can build complex structures, planets can organize into orbits, stars can form, brains can make memories. Order can appear locally, but it appears by exchanging energy and entropy with the surroundings. A snowflake forms as water molecules arrange into a crystal. That looks like increasing order, but heat is released into the environment. The total entropy, including the surroundings, increases. A plant grows leaves from sunlight, carbon dioxide, water, and minerals. The plant becomes organized, but sunlight is degraded into lower quality heat, and the total entropy of the larger system increases. Life does not violate entropy. Life rides entropy. It uses energy flows made possible by entropy gradients. Sunlight arrives from a hot sun. Earth radiates cooler infrared light into space. Between those flows, life can build temporary order. This is one of the beautiful ideas in thermodynamics. Entropy does not forbid complexity. It explains the cost of complexity. To maintain order, a system must use energy and export entropy. Your body is highly organized. Cells, tissues, organs, electrical signals, chemical pathways, but your body maintains that organization by consuming energy, exchanging heat, breathing, digesting, and releasing waste. You are not an exception to the second law. You are a delicate pattern sustained by energy flow. The same is true of every living thing. A moss cushion, a lichen thallus, a forest, a brain, a city, a civilization. Order can exist, but it is never free. It must be maintained. And maintenance, leaves, traces, heat, waste, radiation, chemical change, entropy increase in the larger world. This gives the arrow of time a deeper feeling. The past is not simply the place behind us, it is the direction where entropy was lower. The future is the direction where entropy is likely to be higher. When we remember the past, we remember special arrangements that left records, photographs, footprints, fossils, brain states, written words, light traveling from distant stars. Records exist because processes happened in a direction that increased entropy overall. A footprint forms when a foot presses into soft ground. The ground is deformed. Energy is dissipated. A record is left. The reverse, a footprint spontaneously pushing a foot upward while the ground smooths itself, is not the kind of process we see. Records themselves depend on the arrow of time. This is why entropy is not only about engines and gases. It reaches into memory, causality, history, the feeling that one moment follows another. The reason we can have evidence of yesterday, but not tomorrow. A photograph stores information about a past arrangement of light. A fossil stores information about a past organism. Your memory stores information about previous experiences. Each record is a physical system that has been changed by an event, and those changes occur along the thermodynamic arrow. Entropy gives the world a direction in which records can form. Now, entropy can be confusing because people sometimes imagine it as a force, as if entropy pushes objects around. But entropy is not a force like gravity. It is a statistical measure. It describes how many ways a system can be arranged. The second law says that in an isolated system, entropy tends to increase. The word isolated matters. An isolated system does not exchange energy or matter with its surroundings. The universe as a whole is often treated as the largest isolated system, though cosmology adds subtle questions. Within the universe, smaller systems can decrease their entropy if they increase entropy elsewhere. A freezer can make water into ice, but it releases heat into the room. The ice becomes more ordered. The surroundings become more disordered by a larger amount. The total entropy rises. This is how local reversal is possible. You can unmix in limited ways if you do work. You can separate chemicals, you can build structures, you can clean a room, you can repair a broken object. But each act requires energy, information, and interaction with the environment. The arrow of time is not saying no local order can ever be restored. It is saying that total accounting has a direction. There is always a cost. This cost is why the world does not spontaneously repair itself for free. A broken glass can be replaced or melted and remade, but that requires energy, labor, heat, machinery, and changes elsewhere. The atoms can be rearranged into a cup again, but not by simply waiting in a quiet room. Waiting usually allows the more probable direction to continue. Dust settles, heat spreads, chemicals mix, materials age, entropy keeps its slow ledger. The arrow of time is written in that ledger, not as a ticking clock, not as a visible line, but as the tendency of systems to move toward macrostates, with more microstates, more ways to be, more possibilities hidden under the same large-scale appearance. This is why entropy is the hidden direction. It explains why time seems to flow from intact glass to broken glass, from separated milk and coffee to mixed coffee, from hot tea to room temperature tea, from concentrated scent to diffused scent, from special arrangements to common ones. And yet, one question still remains. Why are there so many more disordered or mixed states than ordered ones? Why is disorder more likely? Why does probability favor the future we actually see? To answer that, we need to look more carefully at counting. Not counting one or two possibilities, but counting the unimaginable number of ways particles can be arranged. Because once we see how large those numbers become, the arrow of time begins to feel less like a mystery and more like a quiet mathematical inevitability. Disorder is more likely for a simple reason. There are more ways to be disordered. That sentence sounds almost too simple, but hidden inside it is one of the deepest ideas in physics. When a system has many particles, many pieces, or many possible arrangements, some large-scale states can be produced in only a few ways. Other large-scale states can be produced in enormously many ways. The states with more possible microscopic arrangements are more likely. This is the quiet engine behind entropy. Imagine a small box divided into two halves. Inside the box are 4 particles. To make the idea simple, let us imagine each particle can be either on the left side or the right side. With only 4 particles, the possibilities are easy to think about. All 4 could be on the left, 3 could be on the left, and 1 on the right. 2 could be on the left, and 2 on the right. 1 could be on the left, and 3 on the right. Or all 4 could be on the right. If we only describe the big picture, we might say there are 5 possible macrostates: 4 left, 3 left, 2 and 2, 1 left, 0 left. But when we look more carefully, the middle state can happen in more ways. 2 particles on the left and 2 on the right can occur with many different combinations. Particle 1 and 2 could be on the left, or particle 1 and 3, or particle 1 and 4, or particle 2 and 3, and so on. The exact identities can vary, while the large-scale description stays the same. By contrast, all 4 particles on the left has only one basic arrangement. Every particle must be on the left. That is a very special condition. Even with only 4 particles, the balanced state is more likely than the all-left state. Now increase the number of particles, not 40, not 4,000. Imagine a gas with trillions upon trillions of molecules. The difference becomes overwhelming. The number of ways to have the gas spread throughout the box is unimaginably larger than the number of ways to have all the gas gathered in one corner. So the gas spreads, not because each molecule has a plan, not because disorder is magical, but because spread-out arrangements outnumber clustered arrangements by an absurdly large amount. The universe is, in this sense, a patient gambler. It does not need to prefer disorder emotionally. It simply moves through possible arrangements, and the common arrangements dominate. A shuffled deck of cards gives another useful picture. There are 52 cards in a deck. A perfectly ordered deck is special. Ace 2 king, suit by suit, or whatever order you define. There may be only one exact arrangement that counts as perfectly ordered, but the number of possible arrangements of 52 cards is enormous. It is 52 factorial. That means 52 times 50, 1 times 50, continuing all the way down to 1. The result is a number with 68 digits, so large that if you shuffle a deck thoroughly, The exact order you create has probably never existed before in the history of cards. Most arrangements look random. Very few look ordered. If you start with an ordered deck and shuffle it, you almost certainly move into a random-looking arrangement. If you keep shuffling, you almost certainly stay in random-looking arrangements. You do not expect the deck to return naturally to perfect order. It could happen in principle, but the probability is so tiny that waiting for it would be a little like waiting for a mountain to write poetry in Morse code. Physics does not need to ban the event. Probability buries it. This is the key. Entropy increases not because order is impossible. Order is possible. Entropy increases because disorder, in a physical sense, corresponds to many more possible A macrostate with many microstates is easier to find. A macrostate with very few microstates is hard to find unless something prepares it. This is why initial conditions matter. A glass is whole because it was manufactured that way. Sand was melted, shaped, cooled, and arranged into a specific structure. Energy was used. Work was done. The entropy state was prepared. Once the glass falls and breaks, it moves toward one of many possible broken states. To get the glass back, more work must be done. The fragments must be collected. The material must be heated, reshaped, and cooled. Order can be restored, but not for free. The same is true of a clean room. A clean room does not stay clean by accident. Objects must be placed in specific locations. Books on shelves, clothes in drawers, papers in folders. Dust removed. The clean state is special because many constraints are being satisfied. A messy room can happen in many more ways. A shirt on the chair, a shirt on the floor, a book on the desk, a book under the bed, dust on the shelf, dust in the corner. There are countless ways for the room to count as messy. This analogy is not perfect physics, because human ideas of clean and messy are subjective, but it captures the counting idea. Order usually means fewer arrangements. Disorder means more arrangements, and systems that are not maintained tend to wander into the larger set. The same idea appears in mixing. Imagine 10 drops of milk in coffee. At first, the milk is concentrated. The molecules are mostly in one region. As time passes, the molecules move through the liquid. They spread. The mixed state can be produced in many ways. The exact positions of the milk molecules can vary enormously, and the cup still looks uniformly brown. But the separated state is special. The milk molecules must be grouped together. The coffee molecules must be elsewhere. That kind of arrangement is rare. The mixed state wins because there are more ways to be mixed. This can feel almost too obvious after you see it, but it took deep work to connect this everyday fact to the arrow of time. The universe does not need to push milk into coffee. Random molecular motion plus probability does the work. The molecules wander, collide, diffuse, and the system drifts toward the macrostate with more microstates. Diffusion is a visible version of counting. Particles spread because spreading has more possibilities. Heat flow is also counting. When one object is hot and another is cold, energy is unevenly distributed. That is a special arrangement. Many units of energy are concentrated in the hotter object. As particles interact, energy becomes shared. There are far more ways for energy to be distributed among both objects than to remain concentrated in one. So energy spreads. The hot object cools. The cold object warms. Eventually, they reach thermal equilibrium. Thermal equilibrium is the state where there is no net heat flow. Temperatures become equal. At equilibrium, the system is not motionless. Particles still move. Molecules still collide. Energy still shifts from one place to another microscopically. But there is no large-scale direction left. No hot to cold flow. No visible trend. The system has reached a high-entropy macrostate, one with enormously many microscopic arrangements. This is why equilibrium feels like an endpoint, not because nothing is happening, but because nothing macroscopic is changing in a preferred direction. The microscopic motion continues beneath the surface. The large-scale arrow has spent itself. A cup of tea cools until it matches the room. After that, it does not keep cooling below room temperature by itself. The temperature difference has disappeared. The gradient is gone. The energy is more evenly distributed. The system has less ability to do useful work. This connection between entropy and useful work is central to thermodynamics. A difference in temperature can drive an engine. A pressure difference can push a piston. A concentration difference can power diffusion. A height difference can drive water downhill. Systems with gradients can do work as they move toward equilibrium, but once everything is evenly spread, the ability to extract work decreases. Entropy increase often means the loss of usable differences. A hot sun and cold space can support energy flow. A battery can power a device because chemical energy is stored in a special arrangement. A stretched spring can do work because energy is stored in its deformation. A living cell maintains chemical gradients across membranes. Gradients are forms of organized imbalance. They are low entropy opportunities. As gradients disappear, energy becomes less available for directed work. This is another way to understand why entropy matters. It is not only about missing, it is about the spreading of energy and the fading of useful differences. Now we can return to time. Time feels like it has a direction because systems with gradients tend to lose them. Special arrangements tend to become less special. Concentrations spread. Temperature differences flatten. Ordered structures break into many possible disorderly arrangements. The future is filled with macrostates that have more microstates. The past is associated with more special conditions. This is why you can often tell whether a movie is being played forward or backward. If you see smoke spreading from a candle, that looks forward. If you see smoke gathering itself into a narrow stream and entering the candle flame, that looks backward. If you see waves in a pond spreading outward after a stone falls in, that looks forward. If you see ripples from the edges of the pond, converging perfectly to launch a stone upward, that looks backward. If you see people cleaning a room, that can look forward because energy and effort are being used. But if the room spontaneously cleans itself with no work, no person, no machine, no energy cost, that looks backward. The difference is entropy, accounting. Local order can increase when work is done, but spontaneous order from a large disordered state is not expected. This is why the arrow of time is so reliable in daily life. You are not observing a few particles, you are observing enormous systems. A cup of coffee contains around septillions of molecules. Air in a room contains a staggering number of molecules. A glass contains an astronomical number of atoms. When systems contain numbers this large, probability becomes more than a gentle suggestion. It becomes the world we experience. A fair coin flipped 10 times might produce all heads. It would be surprising, but not impossible. A fair coin flipped 1 trillion times will not produce all heads in any realistic expectation. The larger the system, the more powerful the statistics. Macroscopic irreversibility is born from microscopic numbers. This is one of the most beautiful turns in physics. The arrow of time does not need to be inserted by hand into every microscopic law. It emerges when there are many particles, many arrangements, and a low entropy starting point. The low entropy starting point is important. If a system is already at equilibrium, there may be no obvious arrow inside it. Nothing large-scale changes. But if a system begins in a special state, it almost certainly evolves toward a more common one. A gas begins in one corner and spreads. Tea begins hot and cools. Milk begins separate and mixes. The glass begins whole and may break. The story starts with specialness. Then probability does the rest. So why was the universe special at the beginning? That is one of the deepest questions in cosmology. We will return to it later. For now, the local lesson is enough. Disorder is more likely because there are more ways for it to exist. Mixed states are more likely because there are more ways to be mixed. Spread out energy is more likely because there are more ways for energy to be shared. Broken states are more likely because there are more ways to be broken. Entropy is the measure of that multiplicity, and the arrow of time is the path from rare to common, from prepared to unprepared, from concentrated to spread, from gradients to equilibrium. This does not make the world meaningless. It makes the world understandable. It tells us why work is needed to build, why memory requires physical records, why life needs energy, why engines have limits, why stars burn, why the universe changes. Entropy is not a villain. It is not a cosmic decay monster hiding behind the furniture. It is a statistical fact about possibility, a quiet arithmetic of the physical world. And once we understand that arithmetic, the second law of thermodynamics begins to sound less like a mysterious command and more like a statement about what almost always happens when many particles are left to themselves. In the next scene, we will look directly at that law, the second law, the rule that gives the arrow of time its most famous scientific form. The second law of thermodynamics is one of the most famous laws in physics. It is also one of the most quietly powerful. It does not sound dramatic at first. It does not describe exploding stars directly. It does not look like a force pulling planets through space. It does not tell a particle where to go at each instant. Instead, it gives a direction. In an isolated system, entropy tends to increase. That is the basic idea. A simple sentence, but it reaches almost everywhere. Into engines, into cooling tea, into melting ice, into living bodies, into stars, into memory, into the universe's future. An isolated system does not exchange matter or energy with the outside. Perfect isolation is rare. A teacup is not isolated. It exchanges heat with the room. Your body is not isolated. It trades energy and heat with its environment. Earth is not isolated because sunlight enters and radiation leaves. But the idea of an isolated system is useful. It lets physicists ask what happens when a system is left to itself. No outside work, no outside energy, no careful hand rearranging the pieces, just the system evolving according to its own internal possibilities. The second law says that in such a system, entropy tends to rise. Or, more carefully, entropy is overwhelmingly likely to rise. That word matters. Overwhelmingly. The second law is not quite like a simple rule that says an object must fall downward near Earth because of gravity. It is statistical. It is built from probability, from the fact that high entropy macrostates correspond to many more microstates than low entropy A system left alone will almost certainly move toward the larger set of possibilities, the more common arrangements, the more spread out distributions, the states with more hidden ways to exist. This statistical nature makes the second law both deep and subtle. At the scale of everyday objects, it feels absolute. Tea cools, gas spreads, ice melts, coffee mixes. A room becomes dusty, a machine wears down. The reverse does not happen by itself, but at the microscopic scale, tiny fluctuations can occur. Small systems can briefly move in ways that look like entropy decreases. A few particles may gather by chance. Energy may fluctuate. Microscopic systems can be noisy and surprising, but for large systems, with enormous numbers of particles, the probabilities become so lopsided that the second law becomes practically certain. A single coin can land heads 10 times in a row. It would be surprising, but possible. A trillion coins, all landing heads at once, is so unlikely that we would never expect it. In the same way, a few molecules can fluctuate, but a room full of air will not suddenly gather into one corner. The second law is the law of enormous numbers, the law of probability becoming experience. Consider again a hot cup of tea. The tea is warmer than the room. Thermal energy is more concentrated in the tea. Molecules in the tea are moving more energetically on average. The cup, air, table, and room are cooler. As time passes, energy flows outward. From tea to cup. From cup to air. From tea surface to surrounding air. From warm vapor into the room. Eventually, the tea approaches room temperature. The process has a direction. Hot to cold. Concentrated energy to more spread out energy. Lower entropy to higher entropy. The reverse would be a cup of room temperature, tea spontaneously drawing heat from the surrounding room and becoming hot again while the room cools slightly. Energy would still be conserved, but the process would require microscopic motions to coordinate in a fantastically special way. The room's energy would need to flow inward against the overwhelmingly likely direction. The second law says this will not happen naturally for a large system, not because energy cannot move, but because the high entropy direction is vastly more probable. Heat flows from hot to cold because there are more ways for energy to be shared than for it to remain concentrated. That is the second law in a cup. Now imagine two metal blocks, one hot, one cold. Place them in contact. At first, there is a temperature difference. That difference is a kind of order, a gradient, a usable imbalance. Energy flows from the hot block to the cold block. The hot block cools, the cold block warms. Eventually, they reach the same temperature. At that point, the large-scale heat flow stops. The energy has not disappeared. It has been redistributed. The system has less usable difference. This is why entropy is connected to useful work. A temperature difference can drive an engine. A pressure difference can push a piston. A chemical difference can power a battery. A height difference can drive water downhill. Gradients can do work. But as gradients fade, the ability to do work decreases. The second law tells us that natural processes tend to reduce usable gradients in isolated systems. They move toward equilibrium. Equilibrium is not death in the simple sense of no motion. At equilibrium, particles still move. Molecules still collide. Energy still transfers microscopically, but there is no net large-scale direction. No overall flow from hot to cold. No pressure imbalance pushing a piston. No concentration, gradient, driving diffusion. No visible arrow inside that system. Equilibrium is the state where the system has reached its most probable macroscopic condition. This is why thermodynamics became so important during the study of engines. Steam engines depend on heat flow. Heat from a hot source does work as it moves toward a cooler sink, a boiler, a piston, a condenser, hot and cold, expansion and motion. Work extracted from a temperature difference. Engineers wanted to understand how much work could be obtained from heat. They discovered limits. No heat engine can convert all heat into useful work with perfect efficiency. Some energy must be released to a cooler reservoir. Some energy becomes unavailable for work. This limitation is not caused by poor engineering alone. It is built into the second law. To produce work from heat, a system needs a temperature difference, but the process of using that difference also increases entropy overall. The engine does not escape the second law. It operates within it. A perfect engine, one with no waste at all, is impossible. This is why perpetual motion machines of the second kind cannot exist. A perpetual motion machine of the second kind would take heat from a single reservoir and convert it entirely into work without any other effect. It would be a machine that steals random thermal motion and turns it into endless useful energy. A dream machine. A tiny loophole factory. Physics says no. Not because humans have failed to build it cleverly enough, because the second law forbids it. Useful work requires gradients, and gradients are consumed as entropy increases. There is no free thermodynamic lunch. Even the universe, generous as it looks from a distance, keeps receipts. This may sound severe, but it is also what allows processes to have direction. The second law explains why engines need fuel, why refrigerators require power, why bodies need food, why batteries run down, why stars burn their nuclear fuel, why life depends on energy flow. Every organized process we know is connected to entropy. A refrigerator, for example, appears to make entropy decrease locally. It makes the inside colder. It moves heat from a cold interior to a warmer room. That seems like heat flowing the wrong way, but the refrigerator uses electrical energy to do this. Its motor runs. Heat is expelled into the room. The total entropy of the refrigerator plus the room increases. Local entropy can decrease if entropy increases elsewhere by a larger amount. This is the important loophole that is not really a loophole. It is how order exists. You can freeze water into ice. You can clean a room. You can build a house. You can grow a plant. You can organize a body, you can write a book, you can create a memory. But all of these processes require energy and produce changes in the structure. The second law is not saying order cannot happen. It is saying order has a cost. The cost is paid in entropy. Life is one of the clearest examples. A living organism is highly ordered. Cells maintain membranes. Proteins fold into specific shapes. DNA stores information. Organs coordinate. Brains process signals. A body keeps itself far from equilibrium. If the body reached thermodynamic equilibrium with the environment in the simplest sense, life would stop. So living systems must constantly exchange energy and matter. They take in food, or sunlight, or chemical energy. They release heat. They release waste. They maintain gradients, ion gradients across membranes, chemical gradients in cells, temperature regulation, ordered structures. All of this is possible because life is not isolated. Life is open. It survives by allowing entropy to increase elsewhere. A plant uses sunlight to build sugars. The plant becomes more organized. But sunlight from the hot sun is converted into lower temperature heat, radiated away from Earth. The total entropy increases. An animal eats food and builds tissue, but metabolism releases heat and waste. The total entropy increases. A brain forms a memory, but forming and maintaining that memory requires physical changes, energy use, and heat. The total entropy increases. The second law is not against life. It is the stage on which life performs. Life is a temporary local pattern maintained by energy flow. A candle flame is similar in a simpler way. The flame has structure, it flickers. It glows. It maintains a shape for a while, but it exists only because wax and oxygen react, releasing heat and light. Chemical energy becomes thermal energy and radiation. The ordered fuel molecules are transformed. Entropy increases. The flame is not a violation of the second law. It is a visible pathway of entropy increase. Stars are grander versions of this story. A star shines because nuclear fusion in its core releases energy. Hydrogen nuclei fuse into helium. Energy flows outward. Light escapes into space. The star maintains itself for millions or billions of years because gravity and pressure balance each other. But the star is not eternal. It uses fuel. It changes. It evolves. It sends energy into the cold universe. The sun supports life on Earth because it provides a powerful energy gradient. Hot sun, cooler Earth, cold space. Energy flows through that difference. Plants, winds, weather, oceans, and living systems all exist within the flow. The second law does not simply make things fall apart. It also makes things happen. Without gradients, there would be no engines, no weather, no metabolism, no stars shining into the dark, no arrow for processes to follow. Entropy increase is not merely decay. It is the direction in which usable differences are transformed, sometimes into motion, sometimes into heat, sometimes into life, sometimes into memory, sometimes into starlight. This is why the second law is so connected to time. It defines a direction that is visible everywhere. A movie of a planet orbiting a star might look reasonable forward or backward, but a movie of heat flowing from cold to hot without assistance would look wrong. A movie of smoke gathering into a candle would look wrong. A movie of a dead battery charging itself from room temperature surroundings would look wrong. A movie of ashes returning to a log in flame would look wrong. These processes reveal the thermodynamic arrow, The arrow points in the direction of increasing entropy. But there is another subtle point. The second law depends on the system starting away from equilibrium. If everything were already at maximum entropy, there would be no obvious direction left, no gradients, no change that could do useful work, no hot-tuckle flow, no natural unfolding from special to ordinary. So the arrow of time depends not only on the laws of physics, but also on the initial conditions. A hot cup cools because it begins hotter than the room. Gas spreads because it begins confined. A star shines because matter collapsed into a dense hot object. The universe evolves because it began in a very special low entropy state. That last point is enormous. The second law tells us how systems evolve from low entropy toward higher entropy. But it does not, by itself, explain why the early universe had such low entropy. For that, we need cosmology. We need to ask why the universe started in such a special condition. We will come back to that later in the journey. For now, it is enough to see how the second law gives daily life its direction. A clock measures time, but entropy gives time an arrow. The clock can tick forward because its mechanism dissipates energy. A digital clock runs because electrical energy is used and heat is produced. A mechanical clock runs down because stored energy is gradually transformed. Even the devices we use to measure time depend on irreversible processes. They are not outside the arrow. They belong to it. A battery drains. A spring unwinds. An oscillator loses energy unless maintained. A crystal vibrates in an electronic circuit while energy flows through it. Timekeeping requires physical change. And physical change produces entropy. So when you look at a clock, you are not seeing time itself. You are seeing a controlled, irreversible process. A small machine using energy to count change. The second law is in the background, keeping the ledger. There is something calming about this, if we let it be. The forward motion of time is not random chaos. It has a structure. Heat spreads. Energy flows. Systems relax. T-word. Equilibrium. Special arrangements become common arrangements. Local order appears when energy flows through matter. Stars shine. Weather moves. Life persists. Memories form. All within the thermodynamic direction. The second law is not a dark prophecy. It is a quiet rule of becoming. It says that the world changes in the direction made overwhelmingly likely by the number of possible microscopic arrangements, from gradients toward balance, from concentrated energy toward shared energy, from low entropy toward higher entropy, from special beginnings toward common futures. This brings us to the next puzzle. If entropy gives time its direction in the large world, what happens at the very small scale? Atoms, particles, microscopic interactions. Do they know about the second law? Or does time's arrow appear only when tiny pieces gather into a larger whole? Next, we will look at time at the microscopic scale. There, the universe becomes strange again, and the arrow of time begins to blur. At the microscopic scale, time becomes harder to recognize. Not because time disappears, not because particles live outside reality, but because many of the simple events that happen among atoms and molecules do not carry an obvious arrow. A molecule moves, it collides with another molecule. Energy and momentum are exchanged. The molecules move away. If you could film this tiny event and then play it backward, the reversed motion might still look physically possible. The particles approach, they collide, they separate. Forward or backward, the basic collision can obey the same mechanical rules. This is very different from a shattered glass reassembling on the floor. At the scale of a single collision, the universe does not always reveal which direction is the future. This is one reason the arrow of time is so subtle. It is not written clearly into every small interaction. It emerges when many interactions are gathered together. One molecule bouncing in a box does not look like a story. A trillion molecules spreading through a room begins to look like time. The microscopic world is full of motion. Atoms vibrate in solids. Molecules tumble in liquids. Gas particles fly through space and collide with one another. Electrons occupy quantum states. Photons carry energy. Everything moves, fluctuates, exchanges, and interacts. But if we zoom in too far, the familiar direction of everyday time becomes less obvious. A single particle trajectory can often be reversed. A simple collision can often be reversed. A small ideal system can, in principle, run backward without violating its equations. This property is called time reversal symmetry. In a time reversal symmetric law, the equations still work if the direction of time is reversed and the motions are reversed appropriately. In classical mechanics, many simple systems have this feature: a planet orbiting a star, a ball moving without friction, a pendulum swinging in a perfect vacuum, two particles colliding elastically. If every velocity were reversed exactly, the system could retrace its path. The past and future would be mirror images in the mathematics. Of course, real systems are rarely perfect. There is friction, sound, heat, radiation, air resistance, tiny vibrations, interactions with the environment. These details matter because they spread energy into more and more degrees of freedom. A degree of freedom is a way a system can store or express energy. Motion in one direction, rotation, vibration, internal motion, heat in surrounding air, sound waves, The more degrees of freedom are involved, the harder reversal becomes. A single ball rolling in empty space is simple. A real ball rolling across a floor is not. The ball pushes on the floor. The floor vibrates. The ball warms slightly. Air moves around it. Sound is created. Microscopic irregularities interact. Energy spreads into many hidden channels. To reverse the motion perfectly, all those hidden channels would also need to reverse. The flow of vibrations would need to return energy to the ball. The sound waves would need to converge. The heat would need to flow back. The air would need to move precisely. Every atom would need to cooperate. This is why real-world processes become irreversible, not because the small laws instantly lose their symmetry, but because the number of microscopic details becomes enormous. The arrow of time hides in the details. At the microscopic level, we can sometimes see the reversibility. At the macroscopic level, we lose the ability to track and reverse everything. Entropy appears. The system forgets its special starting point, or rather, we lose access to the information needed to reconstruct it. This connection between entropy and information is important. A low entropy state contains a kind of special information. Gas on one side of a box tells us something specific. A whole glass tells us the atoms are arranged in a precise structure. Separated milk and coffee tell us where different molecules are concentrated. As time passes, that information becomes harder to recover from the large-scale state. The gas spreads, the glass breaks, the liquids mix. The details are not destroyed in a simple magical sense. They are dispersed into microscopic correlations among particles, heat, vibrations, and the information becomes practically inaccessible. This is why the past leaves records, but the future does not. A record is a physical trace of a low entropy event spreading into the world. A photograph, a footprint, a sound wave recorded by a microphone, a memory formed in a brain. Each record is created by irreversible physical change. At the microscopic scale, information may still be woven through the total state, but at the human scale, the useful pattern has moved in one direction, from accessible to dispersed, from simple to complicated, from readable to hidden. This is one way to think about irreversibility, not absolute disappearance, but practical loss. The exact microscopic state becomes too complex to reconstruct. Imagine dropping a single drop of dye into water. At first, the dye is visible as a concentrated shape, a cloud, a streak, a curling thread. Over time, it spreads through the liquid. The dye molecules are still there. None of them has vanished, but the original shape is gone. To recreate it, you would need to know and control the exact motion of all the relevant molecules. The information about the original shape has become distributed through the entire system. It is no longer available in a simple, visible form. This is what happens with entropy. Patterns dissolve into microscopic detail. The universe keeps the bookkeeping, but not in a way we can read easily. The microscopic world also introduces quantum mechanics. Quantum mechanics complicates the story, but it does not erase the main idea. At quantum scales, particles are described by wave functions, probabilities, and states. The evolution of an isolated quantum system is often described by equations that are reversible. The Schrödinger equation, for example, evolves quantum states in a way that preserves information. In principle, if you know the quantum state exactly, you can calculate its past or future evolution. But measurement, interaction with environments, and decoherence make the world we observe look classical and irreversible. Decoherence is the process by which a quantum system becomes entangled with its environment so that become effectively unobservable at large scales. That sentence is dense, so we can soften it. A tiny quantum system can hold delicate possibilities, but when it interacts with the huge surrounding world, those possibilities become spread into the environment. The system becomes linked with many other particles. The delicate quantum pattern becomes practically impossible to observe directly. The large world appears definite, classical, irreversible. Again, we meet the same theme. The microscopic rules may preserve reversibility, but interaction with many degrees of freedom creates the error we experience. Quantum mechanics also has its own deep puzzles about time. But for our journey tonight, we do not need to solve all of them. We only need to notice the pattern. Small, isolated systems can often behave in ways that do not clearly choose a time direction. Large, open, interacting systems develop a thermodynamic arrow. The arrow appears when information spreads, energy disperses, and entropy increases. This is why the microscopic scale feels strange. It is close to the level where the basic laws still look symmetrical. The world has not yet gathered enough particles to make time's direction obvious. A single atom does not age the way a cup of tea cools. A pair of particles does not remember a past the way a brain does. A tiny collision does not carry the same irreversible story as a breaking glass. Time's arrow is not usually found in one particle alone. It is found in the relationships among many. This is emergence. Emergence happens when a large-scale property appears from the collective behavior of many small parts. Wetness emerges from many water molecules. Temperature emerges from the average motion of many particles. Pressure emerges from countless molecular collisions. Sound emerges from coordinated vibrations in air. And the thermodynamic arrow of time emerges from the statistical behavior of enormous numbers of microscopic states. A single molecule does not have a temperature in the ordinary thermodynamic sense. Temperature belongs to collections. A single particle does not have pressure. Pressure belongs to many particles colliding with a surface. In the same way, the arrow of time is clearest in collections, in gases, liquids, solids, engines, bodies, rooms, stars, galaxies. The arrow is a collective property, a macroscopic song sung by microscopic motion. This does not make it less real. Wetness is real, temperature is real, pressure is real, sound is real. They are emergent, but real. The arrow of time is also real in our experience. It shapes everything we do. It is just not obvious in the simplest microscopic equations. That distinction matters. Sometimes people hear that microscopic laws are reversible and conclude that time's arrow is an illusion. But that is too quick. A rainbow is not an illusion just because it depends on light, droplets, and an observer. Temperature is not an illusion just because it emerges from molecular motion. The arrow of time is not fake just because it emerges statistically. It is real at the scale where we live. It is the direction in which records form, heat flows, bodies age, and memories accumulate. It may be emergent, but emergence is not emptiness. It is how much of the world becomes meaningful. At the microscopic scale, there are also some exceptions and subtleties. Not every law of physics is perfectly symmetric under time reversal in the simplest way. Certain processes involving the weak nuclear force show tiny violations of time reversal symmetry related to deeper symmetries in particle physics. These effects are real and important, but they are not the main reason glasses break and coffee mixes. The everyday arrow of time is overwhelmingly dominated by thermodynamics, by entropy, by probability, by the behavior of many particles. The weak interaction gives physics a subtle built-in asymmetry. Entropy gives daily life its arrow. For a sleep documentary, that may be the gentlest way to separate them. The microscopic universe has delicate asymmetries. The macroscopic world has an enormous statistical direction. When you watch cream mix into coffee, you are not mainly watching the weak nuclear force choose a future. You are watching countless molecules explore overwhelmingly more probable arrangements. You are watching entropy rise. You are watching the arrow emerge from the crowd. This is why time at the microscopic scale is such an important part of the story. It shows us that the arrow of time is not obvious from the beginning. It must be explained. It must arise. If every tiny interaction simply shouted forward, the puzzle would be easy, but many do not. A collision can look reversible. An orbit can be run backward. A quantum state can evolve reversibly in isolation. And yet, the world of cups, bodies, rooms, and stars moves one way. The mystery is not that time exists. The mystery is how the one-way feeling of time grows out of laws that often seem two-way. Statistical mechanics answers much of this. It says, look at the number of particles. Look at the number of possible microstates. Look at the initial conditions. Look at how energy spreads. Look at how information becomes dispersed. Then the arrow appears, not as a command, as an overwhelming tendency, a direction born from possibility, a quiet inevitability made from numbers too large to imagine. Now, we can connect this to memory. Because memory is also physical. A memory is not a ghost floating outside the body. It is stored in physical structures and patterns in the brain. Synapses change. Neural pathways adjust. Molecules move. Energy is used. Heat is released. Records form. So when we say we remember the past but not the future, we are saying something physical. The past has left records in the present. The future has not. And the reason records point one way is tied to entropy. Two irreversible processes. To the fact that causes leave traces after they happen, not before. This brings us to the next scene. We have looked at particles, collisions, reversibility, emergence, and the blurring of time's arrow at small scales. Now we will return to ourselves, to memory, to cause and effect, to the strange fact that the past feels fixed while the future feels open, and we will ask why. The arrow of time is also the arrow of remembering. You remember the past. You do not remember the future. This feels so obvious that it hardly seems like a physics question, but it is one of the deepest signs that time has a direction. Memory is not just a feeling, it is a physical record, a trace left in the present by something that happened before. A photograph records light that reached a camera. A footprint records the pressure of a foot on soft ground. A fossil records the shape of a living thing from long ago. A scar records a change in tissue. A written sentence records the motion of a hand, a pen, a keyboard, or a machine. A memory in the brain records patterns of activity and physical changes in neural connections. Records point toward the past because the past has interacted with the present. The future has not yet left traces. This may sound philosophical, but it is also thermodynamic. To create a record, something physical must change. A camera sensor absorbs light. A photographic film changes chemically. A notebook receives ink. Sand is pressed into a footprint. Brain tissue changes through electrical and chemical activity. These changes are not perfectly reversible. They involve energy. They involve entropy. They involve interactions that leave a mark. A record is a physical structure shaped by an earlier event. This is why records are part of the arrow of time. They form after causes, not before them. Imagine walking across wet sand. Your foot presses down. The grains move. Water shifts. The surface changes shape. When you lift your foot, an imprint remains. The footprint is a record of your step. Now imagine the reverse. A smooth patch of wet sand suddenly forms a footprint before any foot arrives. Then the footprint pushes a foot upward into the air and disappears. This is the kind of event we never see. It would require grains of sand, water, films, air, muscles, and motion to coordinate in a fantastically precise way. The ordinary event is simple. A cause produces a trace. The reversed event is overwhelmingly unlikely. Here, cause and effect are tied to entropy. The cause is an event in a lower entropy context. The effect is a record formed through physical change and dissipation. Energy spreads, matter rearranges, information is written into the world. But writing a record also creates entropy elsewhere. The footprint may look more ordered than smooth sand in one sense, because it has a recognizable shape. But making it involved irreversible deformation, friction, heat, and movement of water and grains. The total process still follows the second law. This is an important idea. Records can be ordered. A photograph is ordered. A book is ordered. A memory is ordered. But records are created by processes that increase entropy overall. Local information can be written because energy is used and entropy is exported. A hard drive can store data, but it requires electricity and produces heat. A brain can store memory, but it uses metabolic energy and releases heat. A notebook can hold writing, but making and writing in it involves physical work and entropy increase. Information is physical, it has a cost. This connects the arrow of time to the arrow of memory. We remember the past because the present contains records of the past. We do not remember the future because the present does not contain records of events that have not yet interacted with it. The future may be constrained by the present. It may be predictable in some ways, but it has not left records. A weather forecast is not a memory of tomorrow. It is an inference from present data and physical laws. A calendar reminder is not a trace from the future. It is a present record of a plan made in the past. A prediction is not the same as memory. Memory is evidence of what already changed the world. Prediction is a calculation about what may happen next. The difference matters. Memory points backward because records point backward, and records point backward because entropy gives physical processes a direction. Cause and effect are also connected to this. In ordinary life, causes come before effects. A stone falls into a pond, then ripples spread. A match is struck, then flame appears. A sound is made, then echoes return. A key is pressed, then a letter appears on a screen. The cause happens first, the effect follows. This ordering feels so natural that we treat it as part of reality itself. But at the microscopic level, as we have seen, many equations can be reversed. So why does causality feel one way? Part of the answer is that causes create records and effects through entropy-increasing processes. A stone hitting water produces waves that spread outward. The energy of impact spreads into the water. The ripples carry information about the impact away from the point where it happened. A reversed movie would show ripples coming in from the edges of the pond, gathering perfectly at one point and launching the stone upward. Again, not strictly impossible in a fantasy of perfect control, but overwhelmingly unlikely. The spreading ripples are a record of the stone's impact. The pond holds a temporary memory. Then the ripples fade. Energy becomes more spread out. The record dissolves. A sound works in a similar way. When you speak, your vocal cords and mouth create pressure waves in the air. Those waves travel outward. They reach ears, walls, microphones, windows, and objects. Some energy is absorbed. Some is reflected. Some becomes heat. A recording device can preserve part of the pattern. The sound leaves traces because physical systems are changed by it. The reverse would require air molecules, walls, and recording devices to send pressure waves backward in just the right way. This would reconstruct the motion of your mouth before you speak. That is not how the world behaves. The effect follows the cause because the physical trace spreads outward in the entropy increasing direction. Light also carries records. When we look at the moon, we see sunlight reflected from its surface a little more than a second ago. When we look at the sun, we see it as it was about 8 minutes ago. When telescopes observe distant galaxies, they see light that has traveled for millions or billions of years. Astronomy is full of memories made of light. The night sky is not showing us the universe exactly as it is now, everywhere. It is showing us records arriving from the past. Photons leave stars and galaxies. They travel through space. They reach our eyes or instruments. They carry information about earlier events. A telescope is a memory machine built from mirrors, sensors, and time. Again, the record forms in one direction. Light leaves the source, travels, and is detected later. The future light has not arrived. The past light has. This is why looking far away in space is also looking backward in time. The universe stores its history in traveling radiation, but even those records are not eternal. Light can be absorbed, scattered, redshifted, lost in noise. Information can become diluted. Entropy can make records harder to recover. The past leaves traces, but not all traces survive. Memory is fragile because records can decay. Ink fades, photographs yellow, footprints erode, rocks, weather, neural connections change, hard drives fail, civilizations lose archives, even stars burn out. The arrow of time does not only create records, it also wears them down. This gives memory its bittersweet, physical character. To remember is to hold a local pattern against a general drift toward dispersion. A brain maintains certain traces for a while. A book preserves symbols for a while. A fossil preserves a shape for a while, but preservation requires stability, protection, energy, low rates of disturbance. No record lasts forever. In physics, this is not sadness. First, it is thermodynamics. Records are physical structures, and physical structures are subject to change. The past is knowable only through the records that remain. This is why the arrow of time is also the arrow of evidence. Evidence points backward. A broken branch tells us something passed through. Smoke tells us something burned. A crater tells us something impacted. A tree ring tells us about a growing season. A fossil tells us about a body once buried. A cosmic microwave background photon tells us about the early universe. The present is full of clues, but all the clues point toward earlier conditions. We reconstruct history because the world contains records of it. Science itself depends on this. Experiments leave measurements. Detectors leave readings. Photographs capture events. Particles leave tracks in chambers. Geological layers preserve sequences. DNA carries evolutionary information. Without records, science would have no past to study. And without the arrow of time, records would not have the same meaning. The formation of records depends on irreversible physical processes. A detector click is an event. A mark on a plate is a change. A bit stored in memory is a physical state. A notebook entry is ink or pixels arranged by work. The universe becomes knowable because events leave traces, and traces exist because of the thermodynamic arrow. Memory in the human brain is especially interesting. A memory is not stored like a tiny movie in a single place. It involves networks of neurons, synaptic strengths, molecular changes, and patterns of activity. When experiences occur, the brain changes. Connections may strengthen or weaken. Proteins may be made. Electrical activity patterns may be reinforced. The details are complex, and neuroscience is still an active field, but the broad point is clear. Memory is physical. It requires matter, energy, and change. Forming a memory uses energy. Maintaining a brain uses energy. Thinking uses energy. The brain releases heat. It consumes oxygen and glucose. It is not outside thermodynamics. It is a warm, living, entropy-producing organ that can hold records of the past. This is one of the most intimate links between physics and experience. The reason you remember earlier moments of this video is not separate from entropy. The sound entered your ears. Signals moved through nerves. Neural patterns changed. The event left a physical trace. If you are still awake, you may remember the opening question. Why does time only move forward? That memory exists because your brain has changed since the video began. The video became part of your physical present. The future parts of the video have not done that yet. They have not reached your ears. They have not altered your brain. They are not memories. They are possibilities. This is why the future feels open. Not because anything whatsoever can happen. The future is constrained by the present, by physical laws, by probabilities, by energy, by matter. But it does not yet have records, in the present in the same way the past does. The past has happened and left traces. The future has not. In everyday language, we might say the past is fixed and the future is open. Physics makes that statement more subtle. The past is known through records. The future is inferred through laws and present conditions. The arrow of time separates memory from prediction, cause from anticipation, evidence from possibility. There is also a connection to control. We can act toward the future. We can choose to lift a cup, write a note, turn off a light, set an alarm, plant a seed. But we cannot act toward the past in the same way. We can affect future records. We can create new traces. We cannot change the traces that already exist without making new changes in the present. If you tear up a photograph, you do not change the original event. You change a present record of it. If you erase a file, you do not erase the past. You change the physical state of storage media now. The past remains what left the traces. The traces can be lost, altered, or hidden, but changing a record is itself a new event in time. This is another reason cause and effect feel one-directional. Actions create future consequences. They do not rewrite earlier causes. To rewrite the entire past would require reversing the enormous network of records, correlations, and entropy-producing processes that connect events. Not just one object, the whole surrounding world. The air, the light, the heat, the memories, the records, the microscopic details. Time travel stories often imagine changing the past, as if history were a page in a notebook. Physics suggests something far more tangled. The past is not a page stored in one place. It is distributed through the present, in countless records and correlations. To change it would mean changing the physical state of the universe. That is a heavier task than fiction usually admits. Still, the desire to imagine it is understandable. Time feels personal. We live through it, lose things to it, build things within it, and measure ourselves by it. The physics of time is not cold, because it is abstract. It touches every memory we have, every regret, every plan, every photograph, every clock, every mark left by every event. But the science gives us a calm structure. Memory is a record. Records require physical change. Physical change follows the thermodynamic arrow. The thermodynamic arrow comes from entropy. Entropy comes from probability and microscopic arrangements. So the feeling of remembering the past is connected to the same physics that makes tea cool and smoke spread. That is a beautiful and slightly strange thought. The cup of tea beside you, if there is one, cools in the same direction that your memories accumulate. The steam fades in the same direction that causes leaf effects. The room changes in the same direction that this sentence becomes part of the past. Time is not only on the clock, it is in every trace, every transformation, every record, every irreversible change. And now that we have connected the arrow of time to memory and cause, we can widen the view again. Because the deepest version of this question is not just about cups, rooms, brains, or photographs. It is about the universe as a whole. If entropy increases toward the future, then the past must have had lower entropy. And if we follow that idea backward far enough, we arrive at one of the greatest mysteries in cosmology, the early universe, the beginning of the arrow. If entropy tends to increase toward the future, then the past must have had lower entropy. That simple thought leads to one of the deepest questions in all of physics. Why did the universe begin in such a special state? So far, we have followed time's arrow through familiar things: a glass breaking, milk mixing into coffee, tea cooling in a room, a scent spreading through air, a memory forming in the brain. In every case, the direction of time pointed from lower entropy to higher entropy, from special arrangements toward more probable ones, from gradients toward equilibrium. But if we keep following that arrow backward, we do not arrive at ordinary conditions. We arrive at the early universe, the beginning of the story, the first great low entropy condition. At first, this may sound strange. People often imagine the early universe as chaotic, hot, dense, violent, crowded, filled with radiation and particles, a place where everything was packed together far from calm. So it is natural to ask, how could that be low entropy? Isn't a hot, dense universe the very definition of disorder? The answer is subtle. The early universe was hot and dense, but it was also extremely uniform. Matter and radiation were spread out very evenly. There were tiny fluctuations, but compared with the universe today, the early cosmos was remarkably smooth. This smoothness is the key. For ordinary gas in a box, a smooth spread-out state is high entropy. Gas likes to spread. But gravity changes the story. With gravity, matter clumping together can increase entropy. A smooth universe filled with gravitating matter is not the highest entropy state. It is actually a very special one. Gravity wants to amplify small differences. A slightly denser region pulls in more matter. That region becomes denser still. Over time, tiny fluctuations grow. Gas gathers. Dark matter forms, structures. Galaxies form. Stars ignite. Planets appear. Black holes form. The universe becomes clumpy. From the point of view of gravity, clumping is part of entropy increase. This is one reason cosmological entropy is more difficult than entropy in a cup of tea. In a cup of tea, energy spreading evenly is the direction of higher entropy. In the gravitating universe, matter spreading perfectly evenly can be a special low entropy condition. Gravity makes structure, and structure, strangely, can be part of entropy rising. The early universe was smooth in a way that required explanation. It was not just a random mess. It was a highly special starting point. A cosmic deck of cards arranged in an extraordinarily rare order. From that smooth beginning, the arrow of time had room to unfold. Tiny density variations grew. Matter collapsed into the first stars. Stars gathered into galaxies. Galaxies formed clusters. Heavy elements were forged in stellar cores and supernova explosions. Planets formed from disks of gas and dust. Chemistry became richer. Eventually, at least in one small place we know of, life emerged. All of this happened because the universe was not already at maximum entropy. There were gradients, differences, possibilities for energy to flow, and structure to form. The universe began with usable thermodynamic potential, a kind of cosmic stored order. The second law could then do its work. Entropy could increase, while creating the conditions for complexity along the way. This is an important point. Entropy increase does not mean the universe becomes instantly featureless. In fact, because of gravity and energy flows, entropy increase can allow rich structure to form. Stars are born, galaxies assemble, planets cool, weather systems move, life evolves. These things are local structures. They exist because energy flows through them, and because entropy increases overall. A star is not a violation of entropy. It is part of the route by which the universe increases entropy. A planet is not a violation. A living organism is not a violation. A brain making memories is not a violation. There are temporary islands of organization within a larger thermodynamic flow. The early universe gave the flow somewhere to go. One of the strongest pieces of evidence for the early hot universe is the cosmic microwave background. The cosmic microwave background is ancient light. It comes from a time when the universe had cooled enough for atoms to form and light to travel freely through space. Before that time, the universe was filled with a hot plasma of charged particles and radiation. Light scattered constantly. The universe was opaque. Then, about 380,000 years after the Big Bang, electrons and nuclei combined to form neutral atoms. Light could finally move freely. That light has been traveling ever since. As the universe expanded, the light stretched into microwave wavelengths. Today, we detect it as a faint glow coming from every direction. It is like a baby picture of the universe, not the beginning itself, but a very early record, a cosmic fossil made of light. The cosmic microwave background is almost uniform. Its temperature is nearly the same in every direction, but not perfectly. There are tiny variations, slightly warmer and cooler spots. These tiny fluctuations became the seeds of later structure. The galaxies, clusters, and cosmic web grew from small differences in the early universe. This is a beautiful connection. The universe had to be smooth enough to be low entropy, but not perfectly smooth. Tiny irregularities were needed for structure to grow. If the universe had been completely uniform forever, no stars or galaxies might have formed. If it had been too chaotic, too early, the story could have been very different. Instead, it began in a special condition. Smooth, hot, dense, expanding, and lightly textured with small fluctuations. From this beginning, gravity slowly wrote structure into the cosmos. The arrow of time in the universe is therefore connected to expansion, gravity, and initial conditions. The universe expands. Matter clumps under gravity. Radiation cools as space stretches. Stars form and burn. Black holes grow. Entropy increases. At each stage, the direction of time is tied to the fact that the universe began far from equilibrium. The early low entropy state is not fully explained by the second law. The second law tells us what happens after such a state exists. It does not by itself explain why the state existed. This is one of the deepest open questions. Why was the early universe so low in entropy? Why were the initial conditions so special? Why did time's arrow begin pointing the way it does? Physics has ideas. Cosmic inflation may help explain the smoothness and structure of the early universe. Quantum cosmology explores possible origins. Some theories suggest deeper explanations involving the nature of the Big Bang, multiverses, or boundary conditions. But there is no simple final answer that everyone agrees on. The low entropy of the early universe remains one of the profound mysteries behind the arrow of time. This is important to say gently and honestly. Science knows a great deal about how entropy increases, and knows a great deal about heat, probability, particles, engines, radiation, stars, and black holes. But why the universe began in a special condition that allowed time's arrow to exist as we know it is still a deep question. The mystery has not vanished, it has become sharper. The arrow of time in your room tonight may begin with the early universe. The tea cools because entropy increases. Memory forms because records are made through irreversible processes. Stars shine because energy flows from hot cores into colder space. And all of these processes are possible because the universe began in a state with room for entropy to rise. The direction of this very moment is connected to cosmic history. The seconds passing around you are not separate from the first conditions of the universe. This is one of the remarkable things about physics. A cup of coffee and the Big Bang belong to the same story, not metaphorically only, physically. The same thermodynamic arrow connects them. Now, let us look toward the future. If entropy keeps increasing, what happens in the long run? Stars will continue to burn their fuel. Some will become white dwarfs, some will become neutron stars or black holes. Galaxies will continue evolving. New stars will form as long as enough gas remains. But over immense spans of time, star formation may slow. Gas will be used up or locked away. Existing stars will age. The universe may become darker, cooler, more diffuse. Black holes may dominate for extraordinary lengths of time, over timescales far beyond human imagination. Even black holes may evaporate through Hawking radiation, if our current understanding is correct. The far future of the universe is often described in terms of heat death. Heat death does not mean everything becomes hot. It means the universe approaches a state of maximum entropy, where usable energy gradients have mostly disappeared. No large temperature differences. No easily available, free energy. No stars shining as they do now. No engines to run. No processes that can continue in the familiar way. A universe near thermodynamic equilibrium would be quiet in the deepest possible sense. Not peaceful like a sleeping room, but empty of the gradients that make change interesting. Heat death is not an explosion. It is the fading of usable difference. The slow exhaustion of thermodynamic possibility. That may sound bleak, but it is unimaginably far away. So far away that ordinary time comparisons fail. Human lives, civilizations, species, planets, stars, even galaxies, all are brief compared with the longest possible future scenarios. For now, the universe is rich with gradients. Stars still shine, planets still cool, chemistry still flows. Life still acts, memories still form. The arrow is still moving through a universe with structure. We live in the middle of the story, not at the end. That matters, because the arrow of time is not only about eventual fading, it is also what allows anything to happen at all. Without entropy increase, there would be no cooling tea, but also no engines, no metabolism, no weather, no starlight, no memory, no story. A perfectly equilibrated universe would have no usable direction. The same arrow that breaks glasses also powers life. The same law that makes coffee mix also allows stars to shine. The same entropy increase that points toward a distant heat death also gives the present its richness. This is the paradoxical beauty of the second law. It is associated with decay, but it also enables process. It takes away special arrangements, but it also allows temporary structures to form along the way. It makes time irreversible, and therefore makes history possible. A history needs a difference between before and after. Entropy provides that difference. The universe has a past because it began in a lower entropy state. It has a future because entropy can continue increasing, and we live in the moving interval between those two, a place where energy still flows, where records can still form, where stars still burn, where brains can ask why time moves forward. If you look at the night sky, you are seeing many arrows of time at once. Starlight traveling from the past, stars aging in their cores, galaxies evolving, radiation stretching with cosmic expansion, old photons arriving at your eyes. The sky is not a still dome. It is a record of processes, a layered memory of the universe. Some stars you see may no longer exist in the same state. Some light began its journey before human history. Some galaxies are seen as they were millions or billions of years ago. Astronomy turns distance into memory. The universe is full of records because time has an arrow, and among those records, the cosmic microwave background is one of the oldest we can observe. A faint glow from a young universe, a whisper from the time when light first traveled freely, a reminder that the arrow of time stretches far beyond human experience, from the early plasma, to atoms, to stars, to planets, to life, to memory, to this moment, and onward. This is why the question, why does time only move forward, cannot be answered only by looking at a clock. A clock is local. The arrow is cosmic. A clock counts change. The universe gives change its direction. The second law explains the tendency. Entropy explains the statistics. Microscopic physics explains the underlying motion. Memory explains our experience. But cosmology asks why the whole story began in such a special way. That question remains one of the quiet giants of physics. A question standing behind every ordinary second. Why was the universe born with an arrow ready to unfold? We may not yet have the final answer, but we can see the shape of the mystery. The past was lower in entropy. The future tends toward higher entropy. The present is the narrow place where we experience the flow. A cup cools, a star shines, a thought becomes memory. A photon from the early universe crosses a telescope mirror, a clock ticks, and the arrow continues. Now, as we approach the end of this journey, we can bring the story back from the universe to the room around you, back to the quiet present, back to the feeling of time passing. We have followed the arrow through glass, coffee, heat, particles, memory, and the early cosmos. And in the final scene, we will let those pieces settle into one calm picture of time, stillness, and the night. And now, we can return to the quiet question we began with. Why does time only move forward? At first, the answer seemed almost too obvious. Time moves forward because that is simply what time does. Seconds pass, clocks tick, days end, memories gather, the future becomes the present, and the present becomes the past. But physics asks us to look more carefully, because beneath the familiar feeling of time, there is a deeper structure. Many microscopic laws do not strongly prefer past over future. A simple collision can be imagined in reverse. A planet's orbit can be mathematically traced backward. A particle moving through empty space can often retrace its path if its motion is reversed. At the smallest scales, the arrow is not always obvious. And yet, in the world we live in, time has a clear direction. Glass breaks, coffee mixes, tea cools, perfume spreads, ice melts. Footprints form, stars burn. Bodies age, memories accumulate. These are not random examples. They are small windows into the same principle. Entropy. Entropy is not merely mass. It is a measure of how many microscopic arrangements can produce the same large-scale state. A whole glass is special. A broken glass can be broken in many ways. Milk separate from coffee is special. Mixed coffee can be mixed in countless ways. A hot cup in a cool room is special. Shared heat is more common. The future is the direction in which systems tend to move from rare arrangements toward common ones, from special states toward more probable states, from lower entropy toward higher entropy. This is the thermodynamic arrow of time, not a visible arrow floating in space, not a force pushing every particle forward, but a statistical direction, so reliable for large systems that it becomes the world we know. The second law of thermodynamics gives that direction its famous form. In an isolated system, entropy tends to increase. It is a quiet sentence with enormous reach. It explains why heat flows from hot to cold, why engines have limits, why batteries run down, why refrigerators require power, why living things need energy, why records form after events, why memories point backward, why stars shine in the colder space. It is the law that makes irreversible change ordinary. But the second law is not only about decay, it is also about process. Without entropy increase, there would be no useful energy flow, no weather, no metabolism, no engines, no burning stars, no memories, no story. The same arrow that makes smoke spread also allows life to use energy. The same arrow that makes a cup cool also lets a brain record and experience. The same arrow that slowly carries the universe toward equilibrium also gives the present its richness. That is one of the strange beauties of physics. The thing that makes moments pass is also the thing that makes moments possible. We also saw that memory is physical. A memory is not outside the universe. It is a record written into matter. A photograph records light. A footprint records pressure. A fossil records form. A brain records experience through physical change. Records point toward the past because the past has touched the present. The future has not left its traces yet. This is why we remember yesterday, but not tomorrow. The future can be imagined, predicted, planned, feared, hoped for, but it is not remembered. It has not yet written itself into the world. A prediction is not a memory. A plan is not a trace from the future. A calendar is a record made in the past about something expected later. The arrow of time separates evidence from possibility. It gives the past its records and the future its openness. And when we widened the view to the universe, the question became even deeper. If entropy increases toward the future, then the past must have had lower entropy. Follow that idea back far enough, and we arrive at the early universe. Hot, dense, smooth, special, a beginning with room for entropy to rise. That low entropy beginning is one of the great mysteries. The second law tells us how systems evolve from special states toward more probable ones, but it does not fully explain why the universe began in such a special state. The arrow of time may begin in the conditions of the early cosmos, in the smoothness of the young universe, in the way gravity turned tiny fluctuations into galaxies, stars, planets, and eventually life. The story of your cooling tea and the story of the Big Bang are not separate. They are connected by the same thermodynamic direction. A cup of coffee and the early universe belong to the same hidden grammar. That may be the deepest thought from tonight's journey. Time is not only something measured by clocks. A clock is local. The arrow is cosmic. A clock counts change. Entropy gives change its direction, and we live inside that direction. Every breath, every thought, every word heard and then remembered, every shadow moving slowly across a room, every star burning through its fuel, every drop of heat leaving a warm cup, every old photograph holding light from a moment that cannot be entered again. Time passes through all of these. But we never see time directly. We see change. We see records. We see before and after. We see the world moving from the special toward the probable, and from that movement, the feeling of time appears. There is something calming in this, if we allow it to be. The forward motion of time is not just a loss. It is also the condition that lets anything unfold. A song needs one note after another. A story needs before and after. A memory needs an event and then a trace. A life needs change. Stillness can be peaceful, but a universe with no arrow would be a universe with no history, no becoming, no records, no night turning into morning, no question becoming an answer, no moment becoming memory. So perhaps the arrow of time is not only something that carries things away, it is also what allows things to arrive. The future arrives because the present changes. The present becomes meaningful because it leaves traces. The past remains knowable because those traces endure for a while. And all of it rests on the quiet arithmetic of entropy. Now, as this journey comes to an end, the room around you may be almost still, but not completely. Air molecules are moving. Heat is flowing. Your body is using energy. The device playing this video is warming slightly. Light is entering your eyes, while sound is reaching your ears. Neurons are changing. Some part of this story may become a memory. The arrow is still here. Not loud, not urgent, just present. In the cooling of a drink. In the fading of a sound. In the soft passing of a thought. In the way this sentence arrives, then becomes part of what came before. There is no need to hold every detail. You can let the equations drift away. Let entropy become a quiet word in the background. Let the second law rest like a clock you no longer need to watch. The universe will continue its patient motion. Heat will flow. Stars will shine. Memories will form. And time, at least as we know it, will keep moving forward. Thank you for spending this calm journey with Midnight Science. If you are still awake, you can let the final image settle softly. A quiet room. A clock glowing faintly in the dark. A cup cooling beside the window. Distant stars carrying old light across space. And somewhere, beneath everything, the hidden arrow of entropy pointing gently onward. Sleep well, and good night.